Hello, welcome to our webinar, Permanganate for Oil and Gas Applications. We will have Mr. John Bull as a presenter today. I am Liz Mueller, our Direct Marketing Specialist with Carus. A few housekeeping items before we begin. We do have all the phones on mute to help cut down on the background noise. There is a feature in GoToWebinar where you can type in your questions. Please feel free to go ahead and type in those questions as you think of them. We should have time at the end of the webinar today to get to those questions. If we do not have time or don't get to a specific question, GoToWebinar allows us to see your contact information and the direct question that you've asked, and we will follow up with you directly. Also, we will send out a PDF version of today's webinar. Please be on the lookout for that either later this afternoon or tomorrow from myself. Here is a look at our 2016 remaining webinar schedule. We have May 9th, Mr. Darren Scott will present lead and copper control with phosphates. On October 17th, we will have safety and handling of permanganate with Mr. John Bull. November 14th, we will have Permanganate 101, again with Mr. John Bull. And then December 12th, we will repeat that lead and copper controlled phosphate webinar with Mr. Darren Scott. If you're interested in attending any of these, please let us know and I will get you registered. Also, we send out 2 newsletters a year and occasional email blasts. If you're not on those mailing lists, please let us know and we will get you added. With that, I would like to introduce Mr. John Bull. He is currently the Technical Service Manager for the Carus Permanganate Business Group. John has been with Carus Corporation for over 40 years, serving in a variety of sales and marketing positions. The Technical Service Department provides chemistry and applications customer support, including on-site lab testing and plant-scale startup and troubleshooting services. John earned his BA in Engineering from Purdue University, West Lafayette, Indiana. He is a member of the Water Environment Federation, WEF, and the American Water Works Association, AWWA, where he served as the AWWA Illinois Section Chair Board from 1992 to 1993.
All right, thanks Liz, appreciate the introduction. And good morning to all of our attendees in Illinois and West, and good afternoon to all of those who are out east. It's great to have you participating today. I've put together a presentation that really falls into 4 different sections. The first 2 are very brief introductions of the company itself, for those of you who may not be familiar with Carus Corporation, and also with the permanganate products that we are currently offering. And then I'm going to build a foundation for some of the discussions of the applications by talking a little bit about oxidation chemistry and about permanganate chemistry in general. And then we'll just cover very briefly all of the different end-use applications that we see in the downstream refining business and also the oil and gas business. And that's as Liz had suggested, we may have time for some questions and answers at the end of the presentation. So let me start by saying just a little bit of background information on the company itself. First of all, we're a privately held company. The Carus family is still involved in the day-to-day operation of the business, and we've been manufacturing permanganates for about 100 years now. We just celebrated our 100th anniversary, so we have an awful lot of experience in producing and marketing permanganate products. We're located in LaSalle, Peru, Illinois, which is in northern Illinois, about 100 miles west-southwest of Chicago. And we also have an operation in Oviedo, Spain, which covers our European markets as well as some of the rest of the world markets that we sell to. Carus Corporation is the largest single producer of permanganates at one location, and we're the only producer remaining in the Western Hemisphere. So we have excellent access and excellent knowledge to all of the markets that are in North and South America. We focus primarily on chemistries and our core technologies of permanganate products, other manganese products such as manganese dioxide, specifically on oxidation chemistry, as you can imagine. And we do have a sister family of products that we sell to the drinking water industry, which are phosphate-based products. We do not sell to any end-user consumer markets. We are strictly a supplier to industrial markets for water treatment, industrial applications, and for environmental uses. And now a little bit about the permanganate products that we are currently supplying. Permanganate comes in really two separate physical forms, two different physical forms. The first is the traditional crystalline solid material that comes as a powder in drums and packages. And this material we actually manufacture in a variety of different grades, which will vary slightly in their physical form and in their purity. But the two most common grades of permanganate that are used are referred to as technical grade material and free-flowing grade material. And then for about 20 years now, we have been commercially supplying, manufacturing and supplying concentrated liquids to the marketplace as well, referred to as our Carus brand of products. And they are available in two purity ranges. One is 20% minimum, and the other is 40% concentration. And I would just make at this point, I think, a specific note about the dry powdered materials. When you think about this, remember that they would be the most concentrated form of permanganate that can be purchased at greater than 95% purity. And therefore, they're the most reactive. And when you think about handling and storage and safety aspects of permanganate, you'll want to consider that most of the information supplied is about the dry crystalline material and how to store it and use it safely. The two forms are actually two types of permanganate products. The dry material is potassium permanganate with a chemical formula of KMnO4, and the liquid concentrated products are sodium permanganate, whose chemical formula is NaMnO4. As I mentioned a little bit earlier, permanganate is an oxidizing agent, and it is quite stable, which means that we can produce it and deliver it as a powder or as a concentrated liquid to any of the customer locations that would require it. And it's an interesting process because we start with manganese ore, which is primarily manganese dioxide. And in our manufacturing process, we apply oxygen and energy to that ore in order to raise the oxidation state up to the permanganate ion. And when the customer uses the product, they actually go in the opposite direction. They purchase potassium permanganate or sodium permanganate, and they take the energy and the oxygen back out of the product, and at the end up with manganese dioxide solid material as the byproduct of the reaction. Now, in addition to the obvious physical differences of potassium permanganate and sodium permanganate, the primary physical difference is their solubilities in water. So we consider potassium permanganate to have a relatively limited water solubility. And you can see from the chart on the left that at room temperature, which is 25 degrees centigrade on this chart, that the solubility curve shows that you can make a maximum of about 6% concentration, and these are all by weight. You can also see from the graph that as you increase the temperature of the solution, you can dissolve more permanganate into the water that you're making up. So it's not unlike dissolving any type of crystalline product. For instance, sugar in coffee, for instance, you can dissolve more sugar at higher temperature than you can in colder temperatures. But if you look at the graph on the right, you can see the solubility curve for sodium permanganate, and you will notice that when you look at the 25 degree centigrade endpoint, that you can get almost to 60% solubility of the sodium permanganate. So the main difference between the two products is this huge tenfold increase in solubility that you can get by just switching from potassium to sodium permanganate. This is a very common slide that we use to indicate and remind you that when you use permanganate products and you dissolve them in water, that you will see the characteristic pink or purple coloration that indicates that permanganate is present. And you can also see from this photograph that this color, the deepness of the color is related to the concentration of the permanganate in the solution. So as the concentration increases, the color gets darker. And you can see in this picture where we're talking about parts per million or milligram per liter levels of permanganate, you can actually take advantage of this and actually measure how much permanganate is in the solution by measuring how much light absorbance there is for each one of these samples. And we can use that to control what we're doing in the field and know exactly how much permanganate is present. So the purple color is detectable by the human eye down to about 0.2 of a part per million, easily 1/4 to 1/2 part per million. We often use a white background in order to look for that permanganate color, and if there are solids in the sample, we'll filter the solids out and pour the permanganate solution into commonly a white styrofoam cup, and if there's pink color there, you will definitely be able to see it. Now that tells you that there's permanganate present, but it doesn't tell you exactly how much is there, and if you want to know the exact quantity, you can set up and read that color on a standard laboratory spectrophotometer, and once that spectrophotometer is calibrated for known samples of permanganate, you can then take any unknown sample and determine exactly how much permanganate is in that particular sample. Now, permanganate is a card-carrying member of the chemical category called oxidizing agents. And there are quite a number of commercial oxidizing agents of which you may be familiar or in fact have used at one time or another. And it would certainly start with just using the oxygen right out of the air as a readily available but relatively weak oxidant, and then going to the commercially available products such as the ozone oxidizing agents, peroxides, and certainly the chlorine hypochlorite solutions as well as chlorine dioxide. There is also not fully commercialized yet, but a oxidizing agent very similar to permanganate, which is a manganese-based compound, and in this case the ferrates are available, very similar to permanganate, but they're an iron-based oxidizing agent. Now there are some very technical definitions of what an oxidizing agent is, certainly to chemists doing work in the laboratory, but I think that the simplest way to think about oxidizing agents is they're a form of energized oxygen. And when you're using an oxidizing agent, you're taking advantage of that energy and extracting it back out again to accomplish the end-use application that you're trying to achieve. It's not uncommon, I don't think, that we would think about oxidation chemistry as being quite common, and that's because we are surrounded in our atmosphere with a great amount of oxygen. So practically speaking, in nature, oxidizing chemistry was quite apparent. They can be slow oxidation reactions, such as the rusting of iron metal in the presence of the atmospheric oxygen, with the characteristic formation of iron oxide material, which is reddish brown in color. Or they can be very rapid oxidizing chemistries, such as when you have a flame and something that's being combusted. So here in this case I just show an organic material, phenol, that is reacting with oxygen rather violently to produce heat and light. And in a complete oxidation reaction, such as combustion, the byproducts of the reaction will be carbon dioxide and water. In addition to being an oxidizing chemical, permanganates are manganese-based chemical. Manganese is a transition metal right next to iron in the periodic table. And manganese is a very common element in the environment. It's the 10th most abundant element in the Earth's crust. And it has a variety of different end-use applications, including a lot of manganese going into the steel industry, as well as being used as the cathodic material in rechargeable batteries, and of course for making other manganese chemicals, such as permanganate itself. Now, permanganate chemistry, when compared to other oxidizing agents, can be rather unique in the way it reacts with different materials, both inorganic and organic. Permanganate likes to attack organic functional groups, as shown here on this particular chart. And one of the functional groups that permanganate likes to attack very readily are unsaturated organics where there are double or triple bonds present. Now, the interesting thing about an organic material that has a functional group associated with it is that the functional group and the structure of the molecule is often what gives that organic material its characteristic odor, or if it's in water, its characteristic taste, and sometimes it can be a color body so that it can be apparent in terms of color in a water supply. So if you're using an oxidizing agent like permanganate and you're attacking those functional groups, your goal is to destroy or remove the characteristic odor, the characteristic taste, or the characteristic color of that compound, improving the quality of the system that you're working with. So there are a number of organic compounds and inorganic compounds that permanganate will react with. I'm just showing a few samples here of what you might be interested in attacking and breaking down, from aldehydes, such as formaldehyde, to aromatics, such as benzaldehyde, styrene, and phenols. There are many organic nitrogen compounds, many different types of primary amines that will be attacked by permanganate, and then some of the more larger and complicated organic molecules that involve nitrogen, such as acrolein and the rather descriptive putrescine, as you can imagine, would have a very unique odor associated with it. Inorganics, reduced sulfur compounds, are very commonly oxidized by permanganate. In this case, I'm showing hydrogen sulfide and sulfur dioxide. And then the organosulfur compounds, such as the dimethyl sulfides, dimethyl disulfides, and many mercaptan groups that can be destroyed by permanganate, all of which have very apparent and characteristic odors associated with them. Permanganate reactions are to some degree dependent on the pH of the system that you're operating in, although for most of the environmental applications that we use permanganate for, we're working in neutral or only slightly acidic or slightly alkaline pH ranges. So you can see in the first reaction shown on this chart that in the pH range of 3 to 12, permanganate ion, which is the MnO4 ion on the left, shown in a slightly purple color, will accept 3 electrons and be reduced to manganese dioxide solids, which I show here as either brown or yellow golden color, which is the way they would look in an actual field application. These solids then are removed from the system by normal solid separation processes, such as settling or filtration. At the extremes of the pH range, we can change the permanganate reaction, so at very acidic conditions we can get a 5 electron transfer, and at very highly alkaline conditions we can often get a one electron transfer that will take place. But these are usually very specific to end-use applications where those pH ranges are deliberately attained. So oxidation chemistry and permanganate chemistry specifically is a very useful, very interesting chemical process. And I like to lump the commercial end-use applications really into four large categories to make it a little bit easier to think about how permanganate applications are developed. So in the upper left-hand corner, you can see that I'm referencing synthesis reactions. So oxidizing agents are used in many cases to produce other materials, especially organic compounds. And the oxidation step can be one of many steps in the production of those materials. Oxidizing agents can also be used to purify finished products and remove a small amount of impurity at the end. To one degree or another, oxidizing agents tend to be bleaching agents. I mentioned that you can remove the color bodies by oxidizing and destroying the functional groups. And we certainly know that we refer to chlorine bleach in terms of a very common whitening or bleaching type of product that's available on the market. Oxidizing agents are also disinfectants, and in fact, when first investigated in the late 1800s, it was about the time we were learning that bacteria, in particular pathogenic bacteria, were related to disease, and so there was a great deal of activity looking for materials that would destroy the bacteria and other biological processes that we didn't want to have around, and so disinfection became an area of a great deal of research. And then finally, a lot of the commercial applications for oxidizing agents fall into the area of what I would call environmental applications, where we're trying to destroy specific unwanted organic pollutants or control odors. So from that, we can talk a little bit about where permanganate's end-use markets currently are. There's a lot of permanganate is used for the purification of drinking water and for, in particular, removing tastes, odors, and colors from drinking water. Permanganate is also used for municipal wastewater treatment. A great deal of that is for destroying reduced sulfur compounds and organic nitrogen compounds that are creating nuisance odors. The odor control can also be not only for municipal wastewater treatment processes, but also on industrial wastewater treatment processes as well. Also on industrial wastewater treatment processes, there may be specific organic materials that are regulated and need to be removed from the system before the water is discharged to the environment. And permanganate may play a role in destroying some of those particular types of materials as well. There's a lot of applications for treating different types of ponds and lagoons where wastewater may be collected or other water systems may be involved. And so we see a lot of applications for treating, for instance, landfill leachate to remove organics and also control odors, and controlling odors from other industrial wastewater lagoons. In the other environmental application areas, permanganate is used to treat contaminated soils, to remove cleaning compounds such as trichloroethylene and perchloroethylene. It is used in scrubbing devices, both as a liquid reagent or as a dry reagent for removing low-level contamination in air supplies by passing the air through some type of dry or wet scrubbing system. And, of course, for a variety of different wastewater treatment processes. Permanganate is used for synthesizing and producing other organic materials, and the largest single use historically for permanganate was for the production of saccharin, which was an artificial sweetener. And I mentioned that permanganate can be used to purify other finished products. The common ones for permanganate use are the purification of carbon dioxide, food-grade carbon dioxide, and also for treating medicinal nitrous oxide, which is used as an anesthetic, and a variety of other inorganic and organic compounds where permanganate is used as a final purification step. And oxidizing agents are used as bleaching compounds. In the case of permanganate, the one that is probably most often referred to now is the destroying the blue indigo dye on denim and producing a white or a washed out pattern on different types of blue jean materials that is used by the fashion industry to produce high-end blue jean products. As a therapeutic or as a biocide, permanganate is used by the aquaculture industry to control diseases that might affect fish, crop fish, when they're being raised in ponds and raceways. And then finally, in terms of industrial processes, I wanted to mention the use of permanganate for cleaning metal surfaces, primarily those products that are ferrous metal based or specialty alloy based. And in the production of these materials, especially in the production of rod and wire, the production process can often leave a scale that forms on the surface of the material, on the surface of the rod or wire. And it was found that hot caustic permanganate solutions can be used to precondition that scale and make it easily removed when you transfer the material from the permanganate and into sort of a standard acid cleaning bath for these products. The goal here is to remove the scale from the surface of the metal and produce a nice clean surface in a lot of cases so that you can do some type of decorative coating or plating on the surface of that material and not have any imperfections that occur later on down the line. This chemistry was later translated and is used now also to treat plastic materials, to clean them, and also to etch them slightly, again, so that you can use a plating process later to plate metal onto these particular types of plastics. This is very common at the printed circuit board industry, where it's necessary to plate copper onto the surface of these multi-layered circuit boards so that you can form electrical connections with no imperfections in the finished product. And this chemistry then has also been taken to other industrial processes where you want to clean scale or remove material from the surface of metal equipment or processes. So the airline industry uses caustic permanganate solutions to remove scale from the hot portions of jet engines so that those jet engines can be later inspected and maintained, looking for any type of corrosion cracking that may be occurring or weaknesses in any of the metal parts. Permanganate is used to remove scale from the hot sections in nuclear power plants, and also it is used to remove organic scaling from different types of process equipment, in particular heat exchangers, where the high temperatures can produce an organic scale that interferes with the heat exchange. And I'll bring this all together by saying this is one of the reasons why you see permanganate being used to remove pyrophoric iron scale in the refining business, because of this long history of permanganate being used not only to remove scale that forms on the inside of equipment, but also in its oxidation of reduced sulfur compounds as well. So let's look specifically at some of the contaminants that the permanganate products are used to remove in refineries. So I just mentioned the use of permanganates for oxidizing and destroying pyrophoric iron scale that forms on the inside of different unit processes in the refinery applications. And of course, also pyrophoric iron can be found in different types of systems where you're pumping crude oil around and treating also produced water. And it's necessary to, if that pyrophoric iron is removed from the water system, to oxidize and destroy that material when it's present. Permanganate's been used in the refinery business to destroy phenols in wastewater, which would be a specific regulated organic material. And of course, hydrogen sulfide, from both a nuisance odor, but also primarily from a safety standpoint. It's important to control hydrogen sulfide emissions and protect the workers in the particular area where it's being released. The organic sulfur compounds, the thiols and the mercaptans, lend themselves quite nicely to control by oxidation chemistry. And then we also have different types of specific pollutants that can be controlled by permanganate, such as the oxidation destruction of cyanide material, the destruction of the organic shell that was built around tetraethyl lead so that we can pop the lead out of that organic chelation, and of course the control of different types of amine compounds as well. In one of the earlier slides I showed that the permanganate chemistry and the pH ranges that we are normally working in produces manganese oxide solids, and those solids are very good, very high surface area materials with a slight negative charge, and they're very good at absorbing some positively charged metals. And we see that this can be used to our advantage when treating wastewater systems where metals removal is an important goal. The permanganate chemistries are used in a variety of different process units when we're trying to remove pyrophoric iron, and an awful lot of permanganate is used currently when it's necessary to clean and repair storage tanks in the oil industry. And that's because pyrophoric iron sulfide as well as hydrogen sulfide are common contaminants present in these materials, and it's necessary to oxidize and destroy them when you're dewatering the tank and separating the solids and going in and cleaning the inside of the tank of any type of scale that may have formed. Spent caustics are very, very high in sulfur material. There also can be a very high permanganate demand if you were to try and treat spent caustics directly just to destroy the sulfide material. But we have shown that when you use an aeration system in the presence of permanganate oxidation chemistry, you can take advantage of that combination treatment to lower the permanganate requirement, make the system more cost effective, and be very efficient in removing the sulfur materials from those types of waste streams. Produced water, I mentioned, is also another area where permanganate is used to treat the pyrophoric irons, and other wastewater applications, including removing equipment scales such as organics from heat exchangers. So many of you are probably aware of how pyrophoric iron occurs and where it occurs within your particular process. But certainly what we have is the sulfide material from crude oils that are reacting with the carbon steel materials in the process, and usually under atmospheres where there is no oxygen present, which allows the formation of these iron sulfide materials. The permanganate can go in and destroy the sulfide, converting the sulfides to sulfates, and it can do this without adversely affecting the equipment itself. There is no corrosion attack of the equipment. There are no toxic gases produced when you're using permanganate in these applications. And it is often an advantage to be able to look for the permanganate color when you're using the permanganate solutions as an indication of when the cleaning process is complete or not complete. So when you start out and you begin to recirculate a permanganate solution, typically in the range of 0.1% or 0.5% to as much as 5%, you will see that characteristic permanganate color, but as it reacts with the materials in the system, that permanganate color will go away. And when the permanganate color is gone, you know that it's time to drain the material out and recharge and start the cleaning process again. But the minute you start seeing the permanganate color persist and no longer disappear, you know that you have achieved your endpoint and the cleaning process can be finished. The only other comment I would make about reacting and removing pyrophoric ions is that it's often a multi-step process because on the inside of the equipment you also will have a lot of oils and petroleum byproducts that will accumulate, and there's no real reason to use the permanganate to remove those. It's easier to use a surfactant wash to get those materials out of there so that the pyrophoric ions can be exposed, and then you can use the permanganate specifically to attack that unwanted material. Another advantage of using permanganate in these particular applications is the speed of reaction. The benefit of permanganate is that it reacts very, very quickly with reduced sulfur compounds, and sometimes there's not a lot of time available in a process, especially let's say if we're dewatering a tank and removing solid material out of the tank and trying to separate the liquids and the solids by using a dewatering device such as a centrifuge. There's not a lot of time available in that system for reactions to take place. And permanganate has an advantage in that it reacts almost instantaneously with the sulfide material. Now I do want to say a little bit about the destruction of phenol compounds that can be present in a variety of different wastewater streams. There's a lot of experience with using permanganate in a variety of different industries that can have phenol as a component of its wastewater stream, and that includes the petrochemical industry, where there's been a lot of work done on permanganate for phenol destruction. In this particular case, the permanganate attack occurs at the alcohol functional group on the phenol ring, and will break the ring open into a long chain carbon compound with a lot of double bond unsaturation in it, and then permanganate will begin to chop that long organic molecule down into much smaller bits, and the end product of those reactions are typically organic acids of very short length. One of the advantages of using permanganate as an oxidizing agent is also that it can be used to precondition these wastewater streams prior to them going to a biological treatment process. You may have a biological process that is acclimated to phenol discharge and removing it very successfully, but biological treatment processes don't react to changes in the system very, very quickly. So if you have a stream where the phenol concentration is fluctuating up and down quite rapidly, or the flows are changing, the biological treatment process may have trouble dealing with the peaks and valleys of that system. Permanganate has been used as a pretreatment to lower the phenol level to a more consistent quantity before discharging it to the final polishing step of a biological treatment process. And permanganate is very forgiving if the biological process is exposed to it, in that the permanganate will not adversely affect the bacteria of the system. What we find is that permanganate is very efficient in destroying phenol. You can remove greater than 99% of the phenol in the system. We typically do not have to change the pH of the system, although if we're trying to drive the reaction much more quickly, we will often raise the pH slightly in order to get the reaction kinetics to go quickly and into completion much more effectively, and that permanganate has been shown to be very cost effective when treating phenol in these types of situations. Now I want to say just a little bit about permanganate safety and using permanganate at different application sites. So there are really three main safety characteristics that you want to be aware of when handling oxidizing agents and permanganate in particular. First of all, when you're working with oxidizers, you're trying to avoid any unintentional mixture of permanganates with reducing substances. And this is why I referred to earlier the fact that a lot of these types of situations occur with the dry crystalline material, which is almost 100% pure potassium permanganate. So those are the products that you want to be handled in the safest and the best possible way. The permanganate products, remember, all oxidizing agents are to some degree disinfectants. So discharging them to the, or releasing them to the environment, they can be considered an aquatic toxicant. And so that's regulated and not allowed to discharge to surface water supplies. And then finally, from the point of view of worker safety, oxidizing agents can be corrosive to sensitive tissues. So we're very much interested in protecting our eyes whenever we're working with permanganate, and also just avoiding breathing the dust or the mist if it's present in the area. So the safety data sheets are available for both the dry crystalline permanganate and for the concentrated liquids. They are all up to date in terms of being GHS compliant, and you can see that they will all refer to the permanganate in terms of its storage and in PPE types of requirements. But you will also see that when you begin to dilute permanganate down with water, that a lot of the hazards associated with handling or using permanganate go away. So water is your friend when you are dealing with permanganate products. And you can see on this particular slide that when the aqueous solution strength is at 6% or less, there really is very little hazard associated with these products. That's true also of the concentrated liquid materials, and you want to be a bit careful when you're dealing with these products, when you're taking care of any type of spill cleanup, because the concentrated liquids can react with combustible materials such as cloth rags or paper towels. And I put this chart together just to try and drive home the idea that the hazards associated with handling oxidizing agents such as permanganate really are directly correlated to the concentration of the material you're working with. So in the case of all those permanganate solutions that are less than about 10% in strength, you really have very little concern about undesirable reactions or any type of special precautions that you have to take care of. But when you begin to increase the concentration, and when we get to the concentrations of the liquid products as they're delivered as 20% or 40% concentration, you can see that we're in the middle section. You want to be a little bit more careful of how you handle and store these materials, and be aware that they can react with combustibles. And then when you get up to nearly 100% as permanganate, as you have in the dry product types of materials, then you definitely have a lot of storage and handling and safety rules that you want to follow and make sure that you're handling it correctly. And in terms of handling permanganate, I mentioned a little bit earlier that Our first concern is always to protect eyes, so eye protection must be worn when handling permanganate products. You want to avoid inhaling any of the dust or mist that might be present, so using permanganate in a well-ventilated area is important. And of course, dust masks can be used to protect yourself when handling dry crystalline permanganate. Avoid contact with skin. The permanganate will react with the oils on your skin and dry your skin out. That can create some cracking and irritation if it's not removed immediately, but in most cases there is no long-term adverse effect with using permanganate and getting it on your skin. Wash your hands with soap and water, and then there are solutions that we can use to remove any types of residual stains that you might be exposed to. And of course, with all chemicals, do not eat or drink any of those materials. So just to close then, in summary, if handled properly and stored properly, permanganate is a very safe chemical oxidant to use, especially when used as a diluted solution in water. It's very effective at controlling reduced sulfur compounds such as pyrophoric iron sulfides, mercaptans, hydrogen sulfide, and also with the destruction of specific regulated organic materials such as phenols and amines. And that permanganate is available both as a dry crystalline product as well as a concentrated liquid in two available concentration forms. And if you have any further questions or any type of technical help that you might need, here is some contact information, and please feel free to let us know, and we'll do our best to answer any of the types of questions that you may have. And now Liz is going to check to see if there are any questions. So if you do have any questions right now, we do have some time to answer those while we have everybody present. So it looks like we have no questions this morning, and thank you very much for attending. If something does come up later on, again, feel free to give us a call or send us an email, and we'll be happy to address those questions specifically for you.